Hello all, welcome to this course, and now let us proceed with the modeling and control of induction machine. Particularly we'll be dealing with the squirrel cage induction machine. So till previous lecture we have seen how we can make use of the frames of reference which are related to the stator and rotor, and then synchronously revolving frame of reference for modeling of the permanent magnet synchronous machine. Now we'll make use of little bit extended equations and little bit extended frame of reference for the induction machine, and then we'll be proceeding with the model. So there are certain basic terminologies which we need to understand before we can proceed with the modeling itself. So once again, if we revisit the equivalent circuit of symmetrical machine, we have indicated the current and voltage and then all other circuit parameters in the equivalent circuit. So essentially the point what we are trying to explore over here is we are trying to define the inductance and the flux associated with different parts of the machine. So as we understand that there is Lm which is defined as magnetizing inductance. So which means the current associated with Lm is basically responsible for magnetizing the air gap flux. So we can say that the current flowing in this branch results into air gap flux. So inductance times of the current flowing through that. Now, as we proceed further, we have different parts associated with the machine. We have the stator, we have the rotor, and when we are talking about the air gap flux, we are essentially talking about the flux which is linking the stator and rotor. Now, if we have to define the flux associated with the stator, which means the stator flux, we need to define first the stator inductance. Now, the other circuit element which is available in our equivalent circuit is basically stator leakage inductance. So we include this circuit element and define what is called as stator inductance, which is basically sum of the magnetizing inductance and stator leakage inductance. So which means it is a factor or circuit element which is involving the common element Lm and the element which is associated with the stator alone. Now we can also define at this point of time a coefficient which is called as stator leakage coefficients. Which we can denote by sigma s, and it is essentially the ratio of leakage with respect to the magnetizing inductance. So stator leakage inductance and magnetizing inductance, the ratio between the two is basically called as stator leakage coefficient. So which means if we have to define our stator inductance in terms of Lm, we can write it as Lm plus sigma s times of Lm, or 1 plus sigma s times of Lm. So these terms would be useful in writing our equations in a compact manner. Similarly, we can proceed and include the rotor leakage coefficient, rotor leakage inductance basically, and we can define rotor inductance, which is sum of magnetizing inductance and rotor leakage inductance. Once again, we have a term which is similar to sigma s, that is called rotor leakage coefficient. This is written as sigma r, and it is ratio of LLR and LM. So LR can be written in a compact manner as Lm times of 1 plus sigma r. Now, having understood these inductance terminologies, we can move ahead and we can include some definitions on the flux side. So we have stator flux, which can be written as psi s. Stator flux is basically sum of the air gap flux plus the leakage flux on the stator side. And we have already denoted air gap flux in terms of Lm and the current Is and Ir, plus sigma Ls, which can essentially be written as combination of leakage inductance and the current associated with that, which is Is. Now, stator flux can be written as, in a compact manner, we can indicate LLS by sigma s times of Lm, and we can take out Lm to write Now it should be noted that because we are dealing with multi-phase quantities, we are eventually going to represent all the quantities in terms of vectors. So we have to denote the stator flux or any other quantity in terms of or as a vector. So here as well we'll be defining a stator flux as a vector, and because this quantity is associated with the stator side, so naturally this will be defined in stator frame of reference. That is also called as the native frame of reference for psi s. Now because it involves current IR, so we need to have superscript for IR indicating that the IR is basically represented in stator frame of reference, but actually this quantity denotes to the rotor frame of reference naturally. Now, once we are having definition for psi s in this manner, it seems as if there is a branch Lm in which there is inductance Lm, in which we are passing a current which is written as combination of Is and Ir along with sigma s. So we can define something called as stator magnetizing current, stator flux magnetizing current, which is basically represented in terms of stator and rotor currents in this manner. So once we have given the definition, now psi s can be written in a very compact manner as IMS times of LM. So it is indicative of that this current is responsible for producing the stator magnetizing flux with the inductance Lm. So one way of representing the magnetizing flux in a compact manner, that is what we have done over here. Now we do have corresponding definitions on the rotor side also. So we have rotor flux psi r defined as combination of air gap flux and the leakage flux on the rotor side. Once again, we can plug in the values of psi m and psi lr. And considering the vector notation, the underscore, this can be written as because rotor flux is a quantity which is associated with the rotor side circuit. So we have the natural frame of reference given as rotor frame of reference. So all the quantities are naturally defined in rotor frame of reference. And since IS stator current belongs to a stator frame of reference, so we have superscript R given over here to differentiate between the two. Now once again, if we plug in the value of LLR in terms of sigma R and LM, we can write psi R in a compact manner and the combination of this current part can be written as IMR, which is our rotor flux magnetizing current. So rotor flux magnetizing current plays very important role in our derivations, and when we are trying to develop the control, it is a very essential quantity over there. Now psi r can be written in a compact manner using IMR and LM in this fashion. Now must be noted that when we are saying a vector IMR, naturally it is represented in rotor frame of reference. So for IMR vector, the natural frame of reference or native frame of reference is rotor frame of reference. Now we will differentiate, we'll draw the different frames of reference and we'll understand how one quantity is transformed to another before getting into the actual equation. So there are now three frames of reference involved in this process. We have stator frame of reference, which is represented as alpha s beta s. So the superscript represents the frame of reference what we are referring to. Alpha beta basically represent the frame of reference which is attached, which is stationary with respect to the quantity. So for example, alpha s beta s would be stationary frame of reference if we are talking from a stator point of view. Then we have the rotor frame of reference alpha r beta r, which means that with respect to stator, this frame of reference is moving with the speed omega m, which is the rotational speed of the rotor, and we are referring to electrical radian per second. So the conversions of number of pole and other quantities are taken care. And at any given point of time, the angle formed by this frame of reference is epsilon. So alpha r beta r is stationary with respect to rotor. So this must be understood. Now, we have seen in case of PMSM that we are trying to represent our quantities in a DC fashion, so that quantities are looking like a DC quantity. So we are defining a DQ frame of reference or synchronously revolving frame of reference. Now here, if I draw a synchronously revolving frame of reference, this is actually moving with the speed omega s with respect to stator. So the speed written over here, omega s, omega m, are basically the speeds with respect to the rotor, or we can say with respect to alpha s, beta s. And the angle formed by this frame of reference is rho. So when we are referring to any quantity which is in rotor frame of reference, which means alpha r, beta r, so quantities, for example, denoted as VR, IR, psi r, these quantities naturally belong to alpha r, beta r. Similarly, we have Vs, Is, psi s, these quantities naturally belong to alpha s, beta s. So IMR is also part of this group only. Now, if we have a quantity in general, say current vector, for example, stator current vector, because we are referring to Is, naturally it is defined in the I alpha s beta s frame of reference. So if we are talking about Is in any other frame of reference, we need to have appropriate frame axis transformation for the quantity Is. Another thing to be noted is that when we are referring to rotor flux oriented frame of reference for our modeling and control, we are essentially targeting that our flux psi r, which is the rotor flux, is oriented along the d axis, which is shown as the synchronously revolving frame of reference. So psi r is going to be aligned along this axis. It may be defined in the rotor frame of reference alpha r, beta r, but by definition, we are aligning our dq axis with or dq frame of reference with psi r. Now, because by definition, psi r is IMR times of LM. So IMR is also oriented along the D axis. However, IMR by definition or naturally it is defined in the alpha r, beta r frame of reference. So these definitions we need to keep in mind while we are dealing with different quantities. So once we have understood the different frames of reference, we also can have a quick understanding of how these angles are associated with the rotational speed. So we have d rho by dt, which is given as omega s, the synchronous speed of rotation. We have d epsilon by dt associated with the mechanical speed of rotation. Now, the difference between the two, say rho minus epsilon, this can be called as the slip angle, which is actually rate of change of that angle is actually same as the difference between omega s and omega m. Eventually, what is popularly known as the slip speed in the induction machine. So this basically gives us the understanding about how slip is going to now come up in the different frame of reference representation. Now going ahead, we need to see how phasor diagram for the induction motor should be modified to include the other quantities which we have defined. So once again, we need to start with whatever is done. For example, we have started with psi m, and we have seen that the voltage vector which is responsible for generating psi m, which is Es, is 90 degree ahead of psi m. We are having rotational speed of omega s in the counterclockwise direction. Then the voltage generated on the rotor side, which is Er, is basically 90 degree lagging with respect to psi m, and there is current Im which is responsible for generation of psi m. The magnetizing current, air gap flux magnetizing current psi m is provided. Now as we go on and load the machine, we will have current on the rotor side, which is denoted by IR, slightly lagging with respect to ER. In total, because there is no other circuit available on the rotor side except R and L, so eventually IR times of IR, IR times of RR, and JIR XLR is going to sum up to give us the value of ER. Now on basis of IM and IR, we can work out what is the current vector on the stator side. So we have minus IR projected on the other side, and the combination of these two vectors, parallelogram sum, is going to give us the stator current vector. Now on basis of this vector, we can write the values of ISRS and J omega XLS, J omega LLS IS, which can give us the supply voltage. Now once we proceed further beyond this, this is what we have done in the previous classes. Now going ahead, we need to have understanding of where the stator flux and rotor flux are going to appear. So we understand that psi s and psi r are basically sum of psi m plus LLS times of IS, and psi r is sum of psi m plus LLR times of IR. So which means we have to add vectors which are along the current vector Is on the psi m to obtain the vector psi s. So if we have the Is vector going in this direction, we need to add a component which is scaled by LLS, and we need to add these two vectors to generate the psi s vector. Similarly, we need to add a vector which is along IR but scaled by LLR, and we need to join these two vectors to obtain the rotor flux vector. Now as seen over here, we have some angle formed between psi s and psi r flux vectors. It can be called as delta. Now referring to the previous phasor diagram or previous frame of reference what we had drawn, we have said that psi r is basically orienting along the d axis, and then all other axes can be worked out. So if we have to project that dq axis on our this phasor representation, we are actually talking about having d axis which is along the psi r, and then of course the q axis is orthogonal to d axis, and this frame of reference is basically rotating with omega s. Now some understanding must be developed at this point of time, is that when we are talking about direct axis, or flux axis, the orthogonal axis is called voltage axis. However, our voltages are not directly aligned along the Q axis because of the IR drop and other factors which are coming over there. So we have our voltage vector little bit shifted from the Q axis. There is certain angle formed by the with respect to the Q axis, and this is coming on account of the loading and other factors which are over there, resistance and loading, etc. Now the other point to be noticed is that the angle formed between the stator and rotor flux vectors is basically a representation of how much load is given to the induction machine. So once again, if we go and recap our basics of the induction machine, what we find is that in case of no load condition or ideal no load condition, the IR is nearly going to go to 0, which means that in this case psi s and psi r are nearly going to be same. The vectors are going to be same, which means that magnitude as well as direction is going to be same, which implies that delta is nearly going to be 0. Now as we increase loading, the value of IR moves up. We have a separation between the psi s and psi r form, which basically represents that the torque is developed as a result of how much separation or how much angle is there between the stator flux and the rotor flux vectors. So in this manner, we can project all the quantities on the frame of reference which is synchronously revolving, and we can see the relative positions of different quantities, how it is obtained over there. So from here, one can always work out the phasor diagram for generator, and it can be seen that by using a similar methodology, the angle between psi s and psi r can be obtained. So once we have developed the understanding of the phasor diagram about the frames of reference and different quantities which are additionally required, we are ready to move ahead with the equations which are related to the stator and rotor. So what we have understood is that for the symmetrical machine, we are writing the stator and stator and rotor KVL in the native frames of reference, and we can define the quantities which are appearing from different frame of reference by having a superscript. Now, because here we have possibility of current flowing on the stator as well as on the rotor side, so which is why both the equations are relevant in our case, in case of squirrel cage induction machine. However, we have a condition that in case of a squirrel cage induction machine, the terminals of the rotor are shorted, which means that our VR vector is going to be 0. It's a 0 vector. Magnitude is not present in that. So what basically we are trying to have over here is that we can simplify this equation to the rotor side KVL, and we can come up with the understanding of how IR can be removed from this equation, because essentially when we are talking about squirrel cage induction machine, there is no possibility of measuring IR. So which is why if we have to work out IR, if we have to work with this model, we need to somehow replace IR with other quantities which are measurable or which can be derived on basis of other measured quantities. So going ahead, we have defined our rotor flux magnetizing current as the combination of IR and IS. Now, because we are saying that we want to remove IR from this equation, we can write IR as IMR minus IS and the whole divided by 1 plus sigma R. Now, it must be noted, as it was said earlier also, the quantity IMR or the vector IMR and IR are represented in the rotor frame of reference, and the quantity IS is transformed to rotor frame of reference. That's why the superscript IR is appearing over there. So we can replace IR with this new equation at all the places in this equation too. Now step by step we can simplify this equation. We can first take out the denominator 1 plus sigma R from the whole equation, and it will result into this term 1 plus sigma R appearing in the last term of this equation. Now this Lm times of 1 plus sigma R is basically Lr. So if we expand the second term, we have possibility of the two terms getting cancelled over here. Now rest of the terms can be expanded once again, and now because this equation does not have any rotor current term, so because this equation is not having any rotor current term and this equation is written in the rotor frame of reference, we would want this equation to come back to the stator frame of reference. So we need to transform to a stator frame of reference because that is more convenient for us in terms of measurement and doing other calculations. However, from the definition we need to see that how IMR can be transformed to stator frame of reference. So once again we will refer to our frame of reference shown over here. What we are trying to do is basically is that quantity IMR is basically defined in alpha R beta R frame of reference, and we want to move it to alpha S beta S frame of reference, which means that we are going in the clockwise direction by angle epsilon. So IMR in the stator frame of reference can be written in terms of IMR, which is naturally defined in rotor frame of reference as IMR times of e raised to power j epsilon. So this is the thumb rule we have seen earlier as well, that if our frame of reference is going in the counterclockwise direction, we have to have a negative angle. But because here we are going in the clockwise direction, so we are having a positive angle over there. Now using this, once we are moving from rotor frame of reference to stator frame of reference, we need to change the quantities appropriately. So we have IMR S times of e raised to power minus j epsilon and Is times of minus j epsilon. Now if we expand this derivative part, we have so once these quantities are out of the derivative term, we can cancel the common term which is available in the equation, and we end up having the equation in the stator frame of reference. Now this equation is written in alpha s beta s frame of reference. So as indicated, we would like our quantities to be DC in nature, and which is why we need to have synchronously revolving frame of reference, which we have written as DQ. And in particular, we are targeting this DQ frame of reference, which is oriented along the rotor flux. Now, once again, if we revisit our different frames of reference, we have defined now the quantity IMRS, which is in the stator frame of reference, and actually this quantity is aligned along the D axis, which means that in the DQ frame of reference, this quantity, if at all it's a vector, or in simpler words, if we see like there is a vector IMR which is rotating at speed omega s, forming an angle rho at a given point of time. So this vector IMR in a stator frame of reference can be represented by having certain magnitude and certain angle. Say this magnitude is IMR, and at this point of time this vector is making angle rho. In general, a vector which is rotating with this speed and forming an angle rho at the given point of time can be represented in this manner. Now it should be noted that the rotor flux magnetizing current IMR is basically a fictitious quantity. It's not an actual current which is flowing in the machine. So, which is why we are free to choose the magnitude IMR for the given current vector IMR. And Angle is given by the position of DQ frame of reference where it is moving. So if we have to talk about this quantity in DQ frame of reference, we essentially need to do the axis transformation, and we can write IMR in DQ frame of reference as the product of IMR vector and e raised to power minus j rho, which is basically the angle found in the counterclockwise direction, or simply because this vector is having only real component which is falling on the d axis, real component only shown over here. So this vector IMR in the DQ frame of reference, so perhaps a DQ script superscript can be written over here, is nothing but just the magnitude IMR, only real component associated with this vector. Hence, if we transform now this equation which is in alpha s beta s domain to synchronously revolving frame of reference, we need to change the quantities to appropriate frame of reference, and then we can use so here all the quantities are written now in DQ frame of reference. Of course, the unit vector is still available over here. So we'll take out this derivative part and we'll simplify it further. So once this derivative term is opened, then we have the common term e raised to power 0, which can be removed from the complete equation. And then we are remaining with terms which are essentially there in the DQ frame of reference. So last two terms can be combined as j times of omega s minus omega m, and rest of the quantities are basically common. So as indicated in this equation, we have IMR which is written in DQ frame of reference. There it is actually aligned along the d axis having magnitude IMR, which is once again defined by us So we need to figure out what is the value of IMR. That will be the task to be done. And then we have IS current vector in the DQ frame of reference, which can be written as ISD plus JISQ in the usual manner. Where IS is the measurable quantity, we can measure the value of IS for all different phases, and we can use axis transformation to obtain the value of ID and IQ, very similar to our previous exercise for the permanent magnet synchronous machine. Now, if we plug in these values in this equation, we have IMR magnitude alone, ISD vector DQ, LR ddt of IMR plus J times of the difference between synchronous speed and mechanical speed, which is actually the slip speed in the induction machine, is going equal to 0 vector. Now, from this equation, we can separate out the real and imaginary components. So we can consider only the real components of this equation first, and we can write IMR minus ISD times of RR plus LR ddt times of IMR is basically going equal to 0. Now, if we rearrange this equation, what we find is that ddt of IMR is actually equal to RR by LR times of ISD minus IMR. Now, this term LR by RR can be defined as the rotor time constant for the machine. So this basically associates with how fast our IMR is settling if we have given a reference or if we have a given command for ISD. So essentially working like a low pass filter. So what basically we have is that d by dt of IMR is equal to ISD minus IMR divided by TR. If we rearrange this equation in S domain, essentially we are going to end up with IMR equal to ISD divided by 1 plus STR. So which essentially means that it is basically a low pass filter having corner frequency at 1 by TR, where input is going in form of ISD and output is rotor flux magnetizing current. So it gives us a way how IMR can be computed on basis of the measured three-phase current. In terms of response, if we see, if there is a step change in ISD, IMR is always going to change according to the time constant of rotor. So we will always see a lag between IMR and ISD. So ISD is the component which is responsible for generating flux in the machine. However, that flux is not immediately achieved. There is a time lag involved with the flux value. And this is where we need to understand that more the value of time constant is, higher the time for settlement in the flux is going to be there. Now taking the other part of this equation, which is imaginary part of this equation. So because IMR doesn't involve any imaginary component, we have imaginary component only with IS dq and the component which is given over here. So we have minus ISQ RR plus omega slip LR IMR, this whole going to 0. Now if we rearrange and write this, this is essentially giving us information about the slip speed in the machine, which is actually proportional to ISQ, inversely proportional to IMR, and the rotor time constant. Now this is very interesting equation because slip speed, as we understand that from the torque slip characteristic, we have slip speed appearing only when there is loading in the machine. If there is no load on the machine, the speed of the machine, induction machine, is going to be very close to the synchronous machine. As we start to load the induction machine, we will find a deviation from the synchronous speed and we will find a lower speed taken up by the induction machine, and that is what is indicative by this component ISQ. So we can say that the ISQ is basically representing the torque component of current, and IMR is basically representing the flux in the machine. So more the torque provided on the machine, more we are going to have the slip in the system. The slip speed is going to be more according to that. So this rotor side equation has given us two important findings, that we can compute the slip speed on basis of the ISQ and IMR, and we can compute IMR from ISD in this manner. So using a simple low pass filter, we can compute the value of IMR from ISD. Now going ahead, we'll be discussing the stator side equations and what more can be obtained from here, and then how to derive the torque for the induction machine. Thank you.